Okay, so now that we have addressed these ideas of how much energy it takes for water to change temperature, for water to change phase, where does that bring us? Why do we care? What's the point of talking about all of that? Well, it turns out that it has a huge impact on climate, right? So think of our planet, and it's mostly water, right? It's about 70% of the surface of our Earth is water. And so there are regions that are close to water and regions that are not so close to water. And those climates are very much regulated by said regions of water. So what's kind of interesting is we get to live that here day to day, right? Which is really quite nice. It makes one of the reasons of being here in California quite awesome. So there are some properties, if we were to compare the differences between water and land, and we're talking about how sunlight comes down into each variable, whether it's water or land, and there are some differences here. Okay, so we're gonna go through those right now. So in this graphic, we can see a couple of things here. We're gonna focus first on the left. So these red arrows are here to indicate the sunlight as it's making its way to the surface. So notice how the arrows don't continue in through land, right? Oops. So there are some things here. So on land, there's low evaporation, not necessarily no evaporation, but it's just much lower. There's generally moisture in soil or in grasslands, and so there can be evaporation that happens there. It's called evapotranspiration. There's no transmission. So what I mean by that is light can't penetrate through the land. So a really a morbid way to think of that. I'm gonna put my face big again. So a morbid way to think about that, but it works, is say you're gonna be buried alive, which is a horrifying thing, of course, totally get that, but you're gonna be buried alive in a plexiglass box. And if you were going to be lowered into a pool, like a swimming pool, and if you were to look up in your box, would you be able to see the sun? You would, right? But if you were to be lowered in the same box, but into the ground, and then Kill Bill style, just like covered with dirt. If you've never seen that movie, by the way, it's excellent. Good old Quentin Tarantino. But you're buried with land, with dirt, and if you look up, would you be able to see the sun? No. So light does not penetrate through rocks or soil, but it does penetrate through water. Granted, it does get scattered, and there gets to be a depth where light does no longer reach a certain distance, but for all intents and purposes, land does not transmit sunlight, but water does transmit sunlight. All right, so just again, morbid, but it works. Land also does not move, right? Excluding landslides or mudslides or earthquakes, land does not move on its own. Land has a really low specific heat, which means that it heats up faster and to a higher temperature than water. And on the other side here, we're looking at a body of water where there's high evaporation, some transmission of light, high mobility, so it moves around very, very easily, and it has a really high specific heat. So this means that the water heats up less quickly and to a lower temperature than land. Another analogy that you can use to think of the differences between these two, and it's way less morbid, I promise, but pretend that you're making some toast and a cup of tea for a snack. So which one will take less time to heat up? You stick a piece of toast into a toaster and you're heating up a kettle of water for tea. Which one's going to take less time? Your toast, right? And then think of, now you have your toast and your tea, num num nums. Which one is going to cool down faster? Your toast, right? So your toast is the land, heats up faster but cools down faster as well, and less energy to do so. Whereas your cup of tea takes a heck of a lot more energy but retains that heat a lot better than your piece of toast. Silly analogy, but again, you take my classes for silly analogies. So here we go. So overall, that actually, climatologically speaking, gives us some really interesting comparisons between cities at the same latitude. So if we were to look at, say, San Diego, California versus Dallas, Texas, where they are at the same latitude, same latitude, so they get the same exact angle of sunlight, meaning they should, in theory, have the same temperature throughout the whole year. Whereas that's actually not the case. So what we're looking at here on the left-hand side is our months on our x-axis and temperature on our y-axis, Fahrenheit on the left, Celsius on the right. And we can see this red line here is for Dallas. And the Dallas line gets much cooler in the wintertime than San Diego, and it gets much warmer in the summertime than San Diego. You can also see it's much more of a bell curve, whereas San Diego looks more like a smaller hill. And again, they are at the same exact latitude at about 33-ish degrees north. So same amount of sunlight, but San Diego has this sweet Pacific Ocean over here, which is keeping San Diego rather mild. Whereas Dallas is in the middle of frickin' nowhere, and so it's not surrounded by water, and so it does not have that natural air conditioner. I did a similar analysis I added in a city of Charleston, South Carolina. So Charleston, South Carolina is again at that same latitude. However, it's still actually next to an ocean. It's next to the Atlantic Ocean this time. So this is East Coast. And we can see that the yellow line here is Charleston. The red is Dallas. The blue is San Diego. But notice with the Charleston line, it is, even though it has still a pretty large range, compared to San Diego, it's still moderate in comparison to Dallas. So it's cooler in the summertime and warmer in the wintertime. And think about where Charleston is. It's on the East Coast and it's next to an ocean, but it's next to a very warm ocean. So the temperatures can fluctuate a heck of a lot more. And that's what this graph here on the right is also trying to show. It's comparing the average temperatures for each location as well as the range for each location. So we can see that San Diego has the smallest range, while on average as a whole, they all actually have on average about the same temperature, which makes sense, again, considering where they are in terms of latitude. So just kind of interesting. So overall, how does water's high specific heat affect Earth's weather? It helps moderate the temperature of land right next to water. It also helps redistribute Earth's heat. So I didn't really go into that second point, but it is a pretty big point as well. The ocean is very mobile, so it can help transport heat from the equator to the polar regions where there's a deficit of energy. And we'll talk more about that later on when we talk about the atmosphere and climate. Moving on from that idea, I want to finish up talking about this term called density. So density, we've talked about this before. It shouldn't be a new word for us. But if we remember what it means, take a second to think back. What does density mean? And density is defined as the physical property of matter that describes the degree of compactness of a substance. So on the left side here, there's more red dots in this box than there is on the right, which would imply that it is more dense. So more dense on the left, less dense on the right, and density is defined here as mass over volume. So the amount of mass that is contained within a certain amount of volume. And the units that we use to describe density is usually in about grams per centimeters cubed, usually. So think about the density of water, right? And think about the density of ice, and think about the density of water vapor. Think about it. Now imagine you have a glass of ice water. Is your ice floating in your ice water, or is it sinking? What's it doing? She floats, right? Ice floats. So what we're looking at here is the temperature of a substance, in this case water, and on our y-axis is density in grams per centimeters cubed. So check this out. 0 degrees Celsius or 32 degrees Fahrenheit is where we have ice, and look at how much it's less dense than that of liquid water, which is water over 0 degrees. So it's in our liquid state, and so yeah, our ice, less dense. There's less green and blue dots here on the left side, and there's more green and blue dots here for liquid water. Even less so for the less dense, the warmer you are, and this is a really important concept as well. So again, looking into this idea of ice and warm water versus cold water, see how there's less red dots in the ice circle, more red dots in the warm water circle, and even more red dots in the cold water circle. So this is implying here that cold water is way more dense than warm water. So that keeps things in the oceans. It's very important. It actually keeps things rather layered. There's not a whole lot of mixing that can occur between the cold water near the lower levels than the warm water at the top. And that's very, very important in terms of productivity, which we'll get to later on. And then here's just another image very similar to the ones we've been showing, just that ice is less dense than water. That's why it floats. It doesn't float completely though, right? It's not straight up on top of the water. There is a little bit of, it's like with the iceberg, right? It's only the tip of the iceberg. Perhaps you've heard that verbiage before. So overall it floats, but it's not like straight up floating on top like a feather would float on top of water. And the last idea I want to bring in here is the role of salt, and what does that play in terms of density. I try to move my face so it's kind of out of the way. That's not really possible with this, so that's okay. So what we're looking at on the x-axis, we'll start over here on the right actually. The x-axis is temperature and the y-axis is density, and the different color lines here indicate more or less salt. So purple is the most salt and red is no salt. And just notice here what salt does. So the saltier the water, the more dense the water is. So the saltier the water, 35 grams per kilogram, the more dense it is. Still gets less dense with a higher temperature, but temperature and salt play a huge role here. And that's what this is trying to show here as well. So the big take-home point with this in particular is that we can actually have water that is below freezing. That's what this is trying to show here. We can have water that is below freezing but not frozen yet. So salt can actually completely change the chemical part of that. And so that's why we can have below freezing water in the Arctic regions where there's sea ice is being formed. So kind of interesting. Interesting and cool, and we'll revamp and re-chat about all of this stuff when we meet again on Thursday. So thanks again for watching, and we'll talk to you soon.